even when we start looking at the Jovian planets themselves and look at the material surrounding them, that's another fascinating, interesting subject. So we can also talk about Jovian moons and rings. So the Jovian planets have some huge, huge moons out there. Galileo himself, when he pointed his telescope up at Jupiter for the first time back in the 1600s, he found that there were these little star-like things which were moving back and forth, which were orbiting around Jupiter. And that was a colossal discovery, because up until that point, Ptolemy's idea, the ancient Greek idea that everything moves in circles around the Earth, was still very much alive. But there's Jupiter. It has moons. It has things orbiting around it. So there's at least proof right there that here's something that doesn't orbit around the Earth. It's orbiting around Jupiter. So Jupiter has 4 large moons. Large moons of Jupiter: Io, Europa, Ganymede, and Callisto. And then we look out, Saturn has a very large moon. Saturn has the moon Titan, which is a fascinating object, and we can go out from there and we can look at moons like Miranda, and Neptune's moon Triton, which is absolutely huge. It's kind of almost like a twin of Pluto. It's a very similar, very interesting, similar sort of object. So for a long time, all we knew was they were out there and you got these moons. And Io orbits around Jupiter every couple of days, and Callisto out there every week or so, and you can observe that, and that's nice. But we didn't have any details about the moons themselves, except some pretty good estimates of their sizes. And so we started doing calculations and thought, well, what are these things like? These aren't gas giants. These are solid objects. They orbit around Jupiter or Saturn and all this sort of thing. And how are they like in terms of size? Are they as big as the Earth? No, they're not as big as the Earth. They're big. Ganymede is the biggest moon in the solar system, but it's not as big as the Earth. It's more closer to Mercury size, and then down from there, and now we understand Mercury. Mercury is relatively small compared to the Earth. All the terrestrial planets started out with molten interiors. They all started out hot blobs of lava orbiting the sun, then they get their crusts, and then they kind of cool off, getting more and more and more solid as you go in. And so what happens is, initially, they could all have a potential for volcanoes, but quickly the smaller ones go solid, whereas the bigger ones, the Earth, Venus, can still have volcanoes today. And so astronomers figured, well, here's what's going to happen when we go out there. We look at Io, Europa, Ganymede, Callisto. We're going to go out there, and since they're Mercury size-ish and smaller, we're going to find that these objects look very much like Mercury. They're just going to be covered with craters. Craters are what happen to a surface when nothing happens to a surface, because you always have objects out there to smash into it and make craters. And so, we'll be able to compare the density of craters on the Moon and Mercury with these moons of Jupiter, and then kind of compare the number of objects out there in the outer solar system. And so we sent first the Pioneers, Pioneer 10 and 11, to just figure out the basics, and sent the Voyager space probes, Voyager 1 and Voyager 2, out to visit Jupiter and Saturn and look at these moons and count the numbers of craters. And it was colossal. It was wonderful. It was totally different than anyone expected. You start taking pictures of things like Io and Europa, and there aren't craters on Io. Well, not impact craters anyway. You look at Io, and it's this fascinating object, but it's nothing like Mercury or the Moon. It isn't covered with craters. And then after a few pictures, they realized they could actually see volcanic plumes erupting out of this. Io is the most volcanically active object in the solar system. Volcanically active. Hugely volcanically active. So there you got Io. Europa has a couple of craters on it, very few, and then moving out, Callisto has a lot of craters, Ganymede has some. And so, why? There's Io. Io is smaller, substantially smaller than Mercury. Mercury, everything in our solar system formed together at the same time out of the same stuff. Mercury went solid, and we have barely any evidence of any volcanism on there at all, because it's small. Its interior cooled off, no liquid interior, you can't make volcanoes. You look at Io and boom, there's volcanoes still erupting today. How could it have held on to its internal heat if it's smaller than Mercury? How quickly you cool off is pretty much an issue of size. So that really threw a monkey wrench into things until people started thinking very carefully about what happens when you're orbiting. Here's Jupiter, and then you got something like Io orbiting right close to Jupiter. And, well, let's see. Let's think about how gravity works. Gravity is a force that gets weaker with distance. So this side of Io, this side over here, feels a stronger force of gravity, and this side of Io feels a weaker force of gravity. It decreases with distance. And so the two different sides of Io really want to orbit in different orbits. They feel different forces of gravity, so they want to move in different ways. And the end effect is to kind of elongate Io, to stretch it out. Now, I'm exaggerating this enormously in order to make a diagram, but as a result, this is what we call tidal. These are tidal forces. Tidal forces are a side effect of gravity. Side effect of gravity getting weaker with distance. Weaker with distance. Because gravity gets weaker with distance, the farther you are from Jupiter, the weaker gravity is, and so different parts of Io, different halves of Io feel different forces of gravity and want to orbit in different ways, and so they try to move in different ways, and that stretches Io, that squashes Io, that stretches it out. And then of course Io is rotating, and sometimes it's closer to Jupiter and sometimes it's farther away from Jupiter, and so the stretching changes. And what does that cause? That causes friction inside Io's interior, because the force of gravity is stretching and squashing Io in different ways. And then there are effects from the moons, so the other, Europa and Ganymede and Callisto, as they go past, they pull on Io in certain ways, and all these gravitational effects cause tidal forces, a side effect of gravity due to the fact that gravity gets weaker with distance. And so as a result, Io's interior gets stretched and squashed and stretched and squashed as it orbits around, and the other things orbit around. And so what happens? All that stretching and squashing in Io's interior causes friction. And friction is a process where you take mechanical motion and you turn it into heat. Friction makes heat. And that's why when they finally got this going and then they ran the numbers, they're like, wow, okay, that's a ton of heat. When you calculate how much friction should come out of the tidal forces stretching and squashing Io, they're enormous. And they're more than enough to keep Io's interior molten. And that's why Io has crazy huge volcanic eruptions going on. Io is the most volcanically active object in the solar system. It has plumes going up so high that if, like, the space station were orbiting around Io, it would have to dodge around the plumes. They go up, hundreds of miles into the air. Absolutely enormous. And so that takes Io and it keeps it volcanically active. And then we go to the next moon, and we go out from Io, and we get to Europa. And I think Europa is the second most interesting object in our solar system. The Earth, of course, is obviously the most interesting because it has life and me, after all. I'm interesting here. But Europa, I got to say that Europa is the second most interesting object in the solar system. It has no volcanoes. No volcanoes. So that's out. But doesn't have craters either. Like one or two. Few craters. So what does that mean? Okay, it means that stuff is happening to the surface, that it's not a dead world. And then what's its surface made of? Its surface is made of ice. Water ice. Good old-fashioned H2O. Water ice. And then you look at the surface and it's all covered with cracks and it's all sorts of, structure going on there. And the fact that it doesn't have craters means, well, craters form. I mean, there's stuff going out there that's going to make craters on Europa, so in order to get craters, you must have to have fresh ice. You must create new ice on top of that. So how do you make fresh ice? Well, you got to have liquid water, and then the liquid water freezes, and hey, liquid water is an interesting thing. And when we do our calculations with Europa, you can see the surface. It's fractured. It's got all these cracks all over its surface. And when we count, well, let's see, how much tidal heating is there from Jupiter? Run the numbers, do the calculations, and you look at that surface, and that's why there are no craters. Occasionally, this breaks, new ice comes out. It's almost kind of like geology here on Earth, except with here, it's liquid rock and solid rock. Out there, it's kind of like with ice. The liquid water behaves like lava out there, comes out on the surface and then freezes. Europa has basically no atmosphere at all, so it really gets out of the surface. It's also going to boil away. But it has this surface of all these cracked, it looks like icebergs and stuff. It's awesome. It's amazing. We run the numbers and probably it could have an ocean. So it's got this thick crust of ice, many, many miles thick. And then underneath it, you can have like somewhere in the neighborhood of an ocean of water about 50 miles deep. When the Galileo space probe went out there in the late 90s and flew past Europa, it very carefully measured the magnetic field around Europa and found that Europa has a magnetic field. Now, it's not going to be from a liquid iron interior. That's not going to make any sense. No, the magnetic field that it has is exactly the sort of thing that responds to Jupiter's magnetic field. It's an induced magnetic field. And it's exactly the sort of thing what you would have if you had a big giant ocean of liquid salt water down there, a liquid conductor, and then responding to the magnetic field of Jupiter. Well, gosh, life formed in our oceans, in the oceans of the Earth, our oceans of liquid salt water. Why not the oceans of Europa's salt water? If our calculations are right, and our measurements aren't completely direct so far, but pretty good. The Galileo magnetic measurements, the calculations, the lack of craters. So we're talking about oceans of salt water, maybe 50 miles deep. It's hard to know exactly, but good grief. And if we understand this correctly, those oceans of liquid water have been there from the beginning of our solar system 4.5 billion years ago. I mean, this is really interesting. Suppose there was no life. Suppose we go out there, send a probe, we go down there, look around. No, there's no living things down there. I think that's amazing. If you can have an ocean of liquid salt water, kept warm by volcanic sort of activity at the base of this bubbling away, and you can have an ocean of liquid salt water and it doesn't form a single blasted living cell after 4.5 billion years. Wow, we just learned something about how rare, how hard it is to form life in the universe. On the other hand, if we went out to Europa and we found something swimming around there, well, golly, that would be kind of cool too. That would keep us busy for a long time. So I think one of the biggest unsolved questions of our solar system is there life in the oceans of Europa? First of all, let's double check, circumstantial evidence pretty good, but does it really have life there? That's really interesting. And then we look at, as we go to Ganymede and Callisto, they have more and more craters, so less tidal heating. Titan, Saturn's moon Titan is an absolutely fascinating object. We sent the Cassini space probe out there, and this is the only moon with an atmosphere. Atmosphere. It has these big clouds. Its atmosphere is mostly made of nitrogen. Very cold out there, but it has an atmosphere of nitrogen. And when we sent the probes out there to take pictures, we discovered there's liquids flowing on the surface today. Liquid on surface today. Not liquid water, much too cold for that, but liquid methane, ethane, liquid hydrocarbons. Methane sort of stuff like that. And if our calculations are right, there's even places where it rains methane and ethane down there. Imagine that natural gas raining from the sky. It's a crazy interesting thing. We see channels, we see all sorts of stuff where there's interesting processes going on there. Titan is a fascinating. We're not thinking life here because life probably requires liquid water, because water is this nice polar molecule that can dissolve things in a way that these kind of more oily substances cannot. But wow, rain and channels and seas and evaporation and clouds, and that's very, very cold out there. Very, very cold out there. But that's something we need to study a whole lot more.